guys, so chapter 4 is going to have 3 videos because it's a longer chapter. So we're going to start this one. We're going to talk about different types of bonding and how to write ionic compounds. All right, this one's a pretty short one and there's not any math, so that's a plus. So the first thing to remember is that elements are just single blocks on the periodic table. But when it becomes a molecule, that's when you have 2 or more elements that combine. And we're going to call molecules compounds specifically. Okay. Also remember that elements could be the same element, just multiples of them. So those are called molecules. And so are compounds. All right. Most molecules are going to be compounds. There's a few of them that will be elements only, but not very many. So when 2 or more elements combine to form compounds, they do get new properties. So we can see here that hydrogen and oxygen are both gases. We know water is a liquid at room temperature. Hydrogen is actually very explosive, and I mean really so is gaseous oxygen, but just pure oxygen. But water is used to extinguish those flames. So remember we talked about the law of definite proportions, and that was just mean that the ratio stayed the same for each compound. So like water is always 2 hydrogens to 1 oxygen, and carbon dioxide is always 1 carbon to 2 oxygens. So that's just saying if I used, instead of water, if I did H2O2, which is hydrogen peroxide, those are the same elements, but they have a different ratio, so now it's a different compound. So there's going to be 3 different types of bonds we're going to discuss. We're really going to focus on the first 2. So a chemical bond is when, or it's what compounds are composed of and how the atoms are held together. Those chemical bonds result in attraction between those particles. Okay, and there are 3 different types: ionic, covalent, and metallic. Again, we're really going to focus on ionic and covalent. Metallic is kind of what it sounds like. So ionic bonding is going to be a metal and a nonmetal, which is super important. You do need to write that down. Covalent bonding is going to be 2 or more nonmetals. So ionic bonds, again, they're between metal and nonmetals, but they do involve transfer of electrons. So the electrons are moving from an atom to another one. In an ionic compound, the metal will always be the cation and the nonmetal will always be the anion. But together, the compound is neutral. Okay, and the reason we've got that cation and anion is because they're attracted to each other through those electrostatic forces because they're opposite charge, because opposites attract. Covalent bonds, on the other hand, are 2 or more nonmetals. So all of those, remember, are going to form anions, which means they don't care as much about charge. So they share their electrons. They do not move them, they share them. Okay, one thing to note, sometimes we call these molecular compounds. I very commonly call them covalent compounds, but both words are going to be used interchangeably when it comes to compounds. The type of bonding is covalent bonding. Okay, and then we're going to talk about different formulas and different ways to show the molecules. So that compound is represented by a formula, and here's some formulas. H2O is water, CO2 is carbon dioxide, NaCl is sodium chloride, and then CCl4 is carbon tetrachloride. I will always write L's in cursive so you know that this is not Ci. I do strongly suggest that you focus on how you're going to indicate it. If you ever see Cl, that is not Ci, it is chlorine. So there are 3 different categories of formulas. There's empirical, molecular, and structural. Empirical formulas give you the simplest whole number ratio. So those are going to be the smallest, kind of like a fraction. It would be as far down reduced as you can get them. A molecular formula, on the other hand, is going to give you the actual number of atoms that you would find in nature. So here we've got C4H8. That would be molecular. This reduced one is empirical. All right, molecular, empirical. Here, we've got molecular and empirical. It is important to know that they can be the same, but they're not usually. A structural formula, that just is a sketch, but it's just a rough sketch. So it's showing you how they're attached to each other instead of just giving you the empirical or molecular formula in this case. All right, so write the empirical formula for each, and they gave us molecular formula. So again, if they give us a molecular formula, you just reduce it. So they're kind of like fractions. Okay, down here, notice A. That cannot be reduced. There is nothing that can go into 5 and 12. So that is molecular and empirical. That one does reduce, B. And C also reduces. This is the common base in most sugars, that's CH2O. Very, very common that sugars have that empirical formula. So again, structural formulas are going to show you the picture. Molecular, the actual number of elements found. And empirical is going to be the smallest whole number ratio. And here we're going to talk about the different models. They do give you colors here because most of the time when you see them, they don't tell you what color is which, but you can tell based on the molecular formula. The space filling model is what mastering really likes to use. The ball and stick model is sometimes shown. You're never going to be expected to draw the ball and stick or the space filling model, but the structural and the molecular you will have to do. The other ones you just have to be able to recognize them. So here is the name of the compound, empirical, molecular, structural, and then the ball and stick model with the space filling model. So real quick, we're going to talk about Lewis dot for elements. Okay, and the Lewis, it is called the Lewis model, but I like to call it the Lewis dot model because we're representing those electrons with dots. And it is only the valence electrons. So remember, those are the A's and B's at the top of each periodic table, at the top of each column. The A's and the B's. Okay, you do follow Hund's rule where they do not pair until they have to. So yes, you see this picture of oxygen. But they go 1, 2, 3, 4, 5, 6. Okay. All right, this slide is just showing us the Lewis model. It's just an easier way to see valence electrons instead of looking at the electron configuration. You can just look at the image. So here, potassium would have A dot. On this one, really this is argon, and so it would be K plus. Notice it has none once it loses this valence electron. Also remember that the noble gases are the most stable on the periodic table. So we use the noble gas configuration, which I did show you in chapter 2. But remember that because the noble gases have 8 valence electrons, most elements are going to want to obey the octet rule, which just means that they have 8 valence electrons, regardless of if it's an atom or an ion. That's going to be the most ideal situation. There are some exceptions to the rule. We'll really get to this in chapter 5, so we'll get to this in chapter 5. All right, it wants us to predict the Lewis model, or use the Lewis model to predict the formula it forms between calcium and chlorine. I'm going to do one this way, and then I'm going to show you the other way. So using the Lewis model, calcium's got 2 valence electrons. Chlorine has 7. Remember, they go single and then they pair. Okay, so in order for everything to have 8, calcium is going to have to give 1 to chlorine. But then you're going to need another chlorine to accept the other one. So when that happens, you've now got calcium 2 plus, and the chlorines gained an electron, so now they're negative. So what you do is that the metals are always going to have no valence electrons. They're going to lose them. The nonmetals will have 8. They go in brackets. And the charges are shown. If there are dots, it must have brackets. Okay, if there are not dots, you can put them, you don't have to. So from this, it wants a formula. This is not the formula, this is the Lewis model. So there are 2 chlorines for every calcium. Okay, so this is CaCl2. There is an easier way to do this. You write the elements, you write their charges. Once you have that, you bring the charges down, and it's called crisscross. And then the plus and minus, they just go away. So this is ClCl2, CaCl2. So that's the easier way. Okay, this bottom one wants magnesium and nitrogen. So magnesium is Mg2 plus. Nitrogen is N3 minus. You do crisscross. So the formula would be Mg3 N2. Okay, so now we're going to do it with the bonding itself. These are just the model versus reality. So the Lewis theory says that ionic solids are going to be really hard, but in reality, ionic solids are pretty brittle. They do shatter when they're struck with something. Also, it predicts that ionic solids don't conduct electricity, but they do conduct electricity when they're in their liquid state or they're dissolved in water. Also, there's a thing called a crystal lattice, and you'll talk about this more in chapter 11. But that crystal lattice is going to be held together by those electrostatic charges for the cations and the anions being attracted to each other. Really, these are only for those ionic molecules, okay, or ionic compounds. It is saying here that there are no true ionic molecules. We call them formula units. All right, this is just going through. You can look at the energetics if you want. We'll really get to this in chapter 9. I'm going to keep going. So here we've got that lattice. This is the crystal lattice structure. Notice they're kind of every other one is the sodium or the chlorine. Here, this is if they conduct electricity. If you put your electrodes into just plain salt that's solid, it conducts nothing. But if you have salt and water, it will conduct electricity. Okay, so just to summarize everything for ionic compounds are always going to contain those negative and positive charges. The sum of those must be neutral. And I know it doesn't say that. It says the sum of the positive must equal the sum of the negative. So it is neutral, but it doesn't specifically say that. Okay. Also, the formula for an ionic compound will be the smallest whole number. So if you need to reduce them, you do. Okay. And again, the smallest unit of ionic compounds is called a formula unit, not a molecule. Now, I'm not going to count it wrong, but they are specifically called formula units. Believe this is our last slide, or our last thing. There may be one slide after this. Here, again, it just wants us to write the formula. Okay, we're going to crisscross, so we're bringing down our numbers. So I've got Ca2O2. But remember, it said the smallest whole number ratio. So really, it should be CaO because they reduce down. Let's do one more. Aluminum, nitrogen. Again, they cross, but notice both the numbers are the same. So if you notice that, we can just write ALN. This only works if they both reduce down. Let's do one like Pb4 plus and O2 minus. We'll get to these transition metal ones in a little bit. But we cross these, I get Pb2O4 But really, this is PbO2. Okay, because they reduce. So if you reduce them, or if they are reducible, go ahead and reduce them. Yep, that's the end of this video. So next video, we're going to be naming compounds instead of just writing their formulas. Y'all have a great day.